Hello, everyone, and welcome to this Surface Ventures workshop. Please say hi in the chat and tell us where you're joining from today. I've seen a couple of people already say hello. Great that you're there, and it seems like hopefully you can hear me. My name is Dr. Sam McMaster. I am the event manager here at Surface Ventures. We are a not-for-profit organization, and our mission is to provide world-class material science education for academia and industry. Today, it is my pleasure to introduce Professor Ben Beake of Micromaterials, who will be our speaker today. After postdoctoral study at Hull, Nottingham, and UMIST, Ben joined Micromaterials, where he's been Director of Materials since 2006. He's a fellow of the IOM3, a past chairman of the IOP Tribology Group, and is currently a visiting professor at Manchester Metropolitan University and the universities of Leeds and Huddersfield. He's very active in collaboration with research with other nanotest users. All right, fantastic. Some great places that people are joining from. Frankfurt. Hi, Ben, of course, from Wrexham. And Quebec, Canada. Fantastic. So many thanks to today's partner, Micromaterials. We'll be releasing poll questions and handouts from them throughout the event, beginning with poll questions. And as we go along, please do type your questions into the chat. They will be marked for the Q&A session, which we will begin after Ben's presentation. We're planning to go for around 60 minutes in total today, and we will be sharing a link for your attendance certificates later in the event. So without any further delay, let's invite Ben on stage and begin the talk. Okay, Ben?
Yep, thanks, Sam.
Okay, fantastic. Let me get your slides up. Brilliant. There you go. Take it away.
Okay, brilliant. Thanks very much. Thanks for the intro, Sam. So welcome and good afternoon, everybody. So I'm going to be talking today about what we've called here a brand new test for assessing erosive wear resistance. So we developed this new test method for small-scale testing of erosion of surfaces in collaboration with Cranfield University and the National Physical Laboratory here in the UK. And if we think about erosion, then solid particle erosion occurs by the stochastic or semi-random impact of many particles, discrete different events on a surface, and you can see bottom left there actually there's an impact surface after a sand erosion of a DLC, and that's actually from Sam's PhD project. And in the middle is a surface of a thermal barrier coating after a high-speed erosion test. And on the right is the sort of thing that we're interested in, is trying to mitigate erosive damage for materials in demanding applications, particularly gas turbine blades in engines that can be subject to particulate erosion in different scenarios that can be, in worst case scenarios, can be life limiting. So if we continue to focus on that application, then the challenge for productivity and sort of towards net zero in gas turbine jet engines is to run them hotter. As these are Carnot systems, so you get more efficient use of fuel, you reduce CO2 emissions just by running hotter. But the challenge is that this is a very demanding application, and you can develop coating systems to provide improved thermal barrier properties, so lower thermal conductivity, allowing you to drop a bigger temperature gradient across the TBC. And these are particularly effective. They allow the superalloy substrates to operate even though the gas is actually above the temperature of the melting temperature of the alloy. But these TBC systems are susceptible to erosive damage. So this is the challenge: is how can we develop efficiently a TBC system that has combined improvement to improved thermal conductivity and resistance to CMAS stack, while maintaining or even ideally improving its impact resistance. So this was the sort of background of the project. So therefore, that said, well, what we need, these are the expensive coatings to develop. We need small-scale test methods that allow us to look at small volumes of material and really try to understand the link between microstructure and performance in these advanced coating systems. So in this presentation, I'm going to start off by introducing a technique that we've called nano impact testing. We've been doing this for more than 20 years. It's quite a successful test at predicting relative erosive wear performance. And then the thing that's new is this new randomized or statistically distributed impact test. So I introduced that for the first time and show how we've got tests on model materials on so-called anomalous and normal glasses, fused silicon Beake 7, and show how for materials that have relatively similar fracture toughnesses, actually the erosion performance of these things is not correlated at all with the fracture toughness for these systems. Then I'll move on to looking at the E-beam PVD thermal barrier coating systems on a superalloy substrate. I'll start off looking a little bit at repetitive tests at the same location. Can we get the same damage from our test that we see in real erosion tests? So we've used focused ion beam imaging to get a handle on that. Then I'll move on to talking about the random or statistically distributed impact tests. And there we wanted to understand how does the type of statistical distribution affect the damage mechanism? What's the effect of the spacing between the impacts and things like that? And does the test qualitatively and quantitatively predict the real erosion rate differences? And then I'll finish off with something we've done more recently, which is to extend all of this to high temperatures, because clearly for the jet engine application, it runs at very high temperatures. So it's very useful if we can do just the same sort of tests conveniently at very high temperatures. So in our test, so we have a nanomechanical test instrument called the Nanotest Vantage, and it's primarily a nano indenter, but it also has it's multifunctional. It has a range of different nano and microscale tribological tests as well, and it can do these in different environments. So one of the things that we developed and patented a long time ago is this ability to do high strain rate indentation tests that we call nano impact. And in these type of tests, we pull the test probe, typically a diamond indenter, off the surface, and we fire it in, and this creates a true impact event, a high strain rate contact. And if you look on the left there, you can see essentially it's something bouncing on the surface, and you get a residual deformation, a rest depth as it's called there. And if you look on the right, there's some examples there with a cube corner indenter on a alumina, technical ceramic. And here you can see that the strain rate does drop through the test because it's a true impact test, but nevertheless you can see those strain rates are really exceedingly high through the majority of that test. So they're much, much higher than you would achieve in normal quasi-static indentation. So you have a real high strain rate test that you can do in this test technique. So we were interested historically primarily with this test as a fatigue simulation tool, essentially, so repetitively cycling the load. And just like you can see on the top right there, that little woodpecker tapping in the way. And after a certain number of impacts, then you get material removal. So this turns out to be a very effective test method to introduce this damage to the surfaces, and also we did it at various different temperatures as well, so it's standard, and it correlates very nicely with erosion. So here's some work from a number of years ago now, and this is some work in collaboration with Rolls-Royce and Cranfield University. And what you can see here is a electron beam PVD deposited thermal barrier coating system of zirconia stabilizing yttria and yttria stabilized zirconia. I always get that the wrong way around. And what we can see here is the effect of thermal aging on the damage tolerance and the erosion susceptibility of this coating system. So when it thermally ages, the damage tolerance that the columns give you is reduced, and there's some intra-column sintering, and that leads to enhanced erosion rates. And if you look on the top right there, you can see the nano impact tests on the same coating systems, and you can see that you get quite a nice qualitative correlation. It's particularly useful because in these type of tests, the small scale tests, the test probe is of a few microns, or in fact, there's maybe a micron or something end radius, and this exactly matches the scale of the columns. So these columns are a few microns in diameter, and this is what happens in this erosion regime. So you've got a test method where you're matching accurately the contact footprint of the test, and this adds to the usefulness for its correlating purposes. So this is some work actually from Sam's PhD quite a few years ago now. And what we're looking at here is 3 different diamond-like carbon coating systems, and they have been different chemistries essentially. One is a standard hydrogenated DLC, another one has been silicon doped, another one has been tungsten doped. And this doping has changed the mechanical properties, and it's changed its impact behavior. If you see on the left there, you can see that it says coating C there, the tungsten doped is a much more resistant coating than the other two. And if you look on the right, you can see the results of individual sand erosion tests that Sam did. So these are very sort of time-consuming tests, and it would be nice if you can use the small-scale test to get all that data and predict nicely just with a few simple impact tests. So this all works quite nicely, but it doesn't quite capture the true nature of what happens in a real erosion situation. So in a real erosive situation, there are discrete events happening at different locations on the surface. So the damage from one impact is affecting the damage later on. So there's a damage accumulation in the materials in the surface. So we've generated or modified our tests so that we can essentially move the sample stage in between doing these repetitive tests. And that allows us to create these different types of arrays of damage, and we can program different statistical numbers of impacts, different distributions, and different array sizes as well. And this turns out to be a very convenient test method. So this is on the right, shows the example with a spheroconical probe, and this is a thermal barrier coating system, and this is the sort of thing, and this would be moving around in between the tests. That's exactly the sort of thing we've done. Okay, so thermal barrier coating systems are inherently extremely complicated, and they're very rough. So they have a remarkably rough surface by nanomechanical test standards, essentially. So, and we didn't want to polish them before testing, so we looked to look at the real surfaces. But before we went on to that, we looked at some bulk standard well-characterized glasses. So here is an example with fused silica. So here we've got 50 impacts within a square millimeter essentially here, with a rectangular distribution used in this case. So an equal probability of any impact happening in any position within that square millimeter. So there's 50 impacts, and you can see they're fairly spaced apart. Maybe there's some situations where 1 or 2 have been affected by the others, but essentially they're discrete. If we run that test on and we do it for 150 impacts, we get something fairly similar, maybe get a little bit more overlap. Run it on a bit more. Now we're starting to get a little bit more regions where suddenly we're transitioning to a more severe damage regime. And we run it on a bit more, and then we're seeing more of that progression of that damage. So that's what happens on fused silica. So fused silica is an aluminous glass. It has essentially a Hertzian cone cracking type dominated cracking pattern. If we contrast what happens now with the borosilicate BK7, so this has a different set of mechanical properties, a different crack morphology. It's actually tougher than fused silica. But if we look to see what happens in our impact test, we can see we're getting this crack morphology joining up between the different impacts, and this is promoting a transition to more extreme damage earlier. And if we run it under exactly the same conditions, we can see by 250 impacts, we're getting large amounts of the surface are starting to be totally destroyed. And if we run it on to 500, we can see there that the whole surface is totally destroyed. So very clear, correlates with what you see in the literature for erosion. So we have a very nice test. But what we have with our instrument being a nano-indenter is we have the ability to monitor the depth throughout the test, and we have various different metrics that we can pull out, quantitative metrics that we can pull out through this test. And this allows us to track the individual damage. So this is just an example of one test. And here we're looking at the probe depth and the velocity, and tracking those as a function of time for a single impact. So the grey region marks the whole of the high speed indentation process, or the impact process. So you reach a maximum velocity at the surface, then you're getting a maximum velocity the other way when it's coming out. And from that, you can track various metrics. You can pull out the coefficient of restitution, residual depth, the kinetic energy absorbed in the process. And these things are all very powerful metrics when it comes to understanding how you can design impact-resistant surfaces. So if we look here to contrast BK7 and fused silica, if we look on the left, we're looking at the residual depth from the impact process. So there's a little bit of cracking on the fused silica, there's a little bit of variability. Depth's around 5 microns. You can see on the BK7 that it starts off fairly similar, but there's an upward trend in that residual depth. And then after about sort of 260 impacts, there's a change to a more severe damage regime, where really we're getting even up to sort of 50 microns of depth per impact. On the right, you can see quantitative kinetic energy absorbed per impact, and you can see again the differences between those two materials. And also it pulls out quite nicely differences in the kinetic energy before that transition. So these again relate to the mechanical properties in the different classes. Another nice one we can look at is the coefficient of restitution. So this one is related to the dynamic hardness to modulus ratio in the material. So there you can see that the fused silica has this higher dynamic HOV ratio, and therefore it produces these more elastic impacts where the coefficient of restitution is closer to 1. And we can track how these things change as a function of conditions as well. And if we run under smaller forces, smaller accelerating distances, we can get coefficients of restitution quite up near 1. And equally, we can get more severe and go further down. So essentially, these are very complicated tests. So we can also design tests where we can simplify things. In this case, we design tests where we control the spacing between adjacent impacts. So in this case, all of these impacts, so there's about 100 there or something like that, are under exactly the same conditions. The only thing that's changed is the spacing. So in this case, this is for fused silica, and this is between, say, starting off 100 microns apart or something, and then moving down to being almost completely overlapping down the bottom. And the spacing between the rows is kept at 100. And what you can see there, if you zoom in on the right, is you can see there's quite a clear, abrupt transition between when they're 70 microns apart. Under these conditions, they don't interact, or they don't appear to interact. And when you take it down to 60 microns, then you're starting to get these cracks joining up between the coating, between the adjacent impacts. So we want to understand a bit more about that. And these are essentially, because they're glasses, they're transparent, that allows us to get more information out of laser scanning confocal microscopy. So here's some work we did, again, particularly with Hanno and Peter at MPL. And here you can see just examples of, on the left is fused silica, and you can see actually that you can see some subsurface information that you can obtain, and these images under green light also, they're quite, so actually these interaction of the Hertzian cone cracks actually create something looking almost like this subsurface straight line. And if you look on the right, you get a very different crack pattern on the Beake 7, so you're getting this much more radial lateral system with this much completely different subsurface crack pattern. And this is the sort of thing that explains these differences in erosion. So these differences are related to the differences in the mechanical properties in the glass, as shown there. And you can see how the ratio of the elastic modulus to the hardness and the Poisson's ratio affect crack systems. So on the right, that's just an example for a Vickers indenter in a quasi-static test. But it seems very much that in our high strain rate dynamic tests with a spherical indenter, we're getting very, very similar differences. Okay, so if we move on now to the thermal barrier coating system. So the sort of standard E-beam PVD system is yttria-stabilized zirconia. It's used for particularly the harshest environments. And you can see it has a columnar structure, these sort of pyramidal tops to the columns. And on the right is one of these candidate zirconates that has lower thermal conductivity, but not necessarily as good erosion performance. And these are sort of two baseline systems to have a look at. So in this case, the gadolinium zirconate, or GZO, on the right has it has a sublayer of yttria-stabilized zirconia underneath as well. So you see these are much more complex systems than the glasses. Excuse me. So if you look at the top, you can see the columnar structure there. It's quite complex. Yttria-stabilized zirconia. On the right, there's a fib cut image going through those columns, and you can see the pyramidal tops. You can see the porosity between the columns, and you can see that in this case they're fairly sort of normally oriented. If we contrast this to GZO, you can see again quite a complex surface here. These canted, if you like, columns. So there's about a 15-degree cant angle. Maybe you can just make it out on the right. And it's a very complex structure. And if we start off by just doing repetitive impact tests at the same position. So under these conditions, this is at the end of sort of 50 impacts, getting quite a large impact crater. It's going across several columns. And what you can see on the left there for the yttria-stabilized zirconia is it's a really sort of compaction-dominated mechanism under these conditions. And on the right, you can see for the gadolinium zirconate, you can see something quite similar, but actually within the middle of that crater, you can see some debris has fallen into that impact crater. So that points to a sort of toughness difference potentially in those two materials. And you can track the depths throughout these tests and different loads as well. And from those depths, you can convert, and this is a new result again on the project, we can convert from the depth data directly to impact volume by taking account of the probe geometry, the elastic recovery in the test, and the contribution of the instrument flame compliance. And we can subtract all of that out and convert to impact volume. So there's some examples there for yttria-stabilized zirconia. This is after a single impact and at the end of the test after the final. You can do this for every single impact you like within the test. And you can see those are very linear regimes, correlation coefficients very near 1. So that's quite a nice thing. So we can do all that without needing even to particularly look at the craters. But there's a lot more information you can get out of looking at the craters, and particularly with the help of Diane at Cranfield and Lewis and Christine, then we were doing some using Fib imaging to do cross sections through those craters. So here's an example, again at 500 millinewtons on the yttria-stabilized zirconia system. And what you see there is the compacted zone in the middle on the left, and it's near the surface region. Then essentially you're getting about sort of 15 or 20 microns of compacted material. And then under that, you can see these cracks going across several columns. And so the blow up on the right, you can see it more clearly. And that's the dominant removal mechanism for in erosion of these seams. So the cracks go across several columns, and then it causes the removal of a large amount of materials. So if we do that same sort of test, but under much more severe conditions, then we can see something quite interesting. We're getting transition to something looking much more like a fatigue type mechanism, where we're now getting this very, very fine scale debris now, this sort of sub-micron debris, and this complete breaking up of the structure. So we're able to do two types of tests here. So the interesting thing, of course, is, well, how does that correlate with the real erosion results? So this is a schematic of the erosion rig at Cranfield that's been around a long time. It's been updated recently. And here, this rig allows the ability to do these very high speed, high velocity erosion tests. So under standard conditions, when you have angular alumina particles around a sort of 100 micron size, this translates into doing erosion tests at around 200 meters per second. So it's quite a complicated thing. So the two main mechanisms that you see are this cracking across the columns, and you get in some locations as well, you get this transition to this more severe mechanism where the whole structure fails. So these are exactly the two mechanisms that we see in a small scale test. So that's for the first time we were able to see that. That's quite nice. So very good. But the next stage was to do the randomized impact test. So as I mentioned, you can do different types of distribution. On the left, you could do a Gaussian distribution where you have a higher probability of your impacts occurring near a central spot, or you could make them equally spaced on the right. So there's an example there just of 500 impacts there. So if we zoom in now, these repetitive impact tests and see at small scale, then under these conditions, you can see compacted regions of the surface. You can see how the damage between the different impacts is starting to progress. But there's untouched material between those impacts. So these are relatively early stages of the impact process. So it's compaction and cracking at the peripheries that are the dominant deformation. So if we compare the two materials, we can see that if you, in a real erosion test, they start off looking quite similar then, but within towards the steady state erosion, then you get a bigger transition and a bigger difference between those two materials. So the yttria-stabilized zirconia is significantly, it's about five times more impact resistant than the gadolinium zirconate. So we wanted to understand a little bit why this gadolinium zirconate was not performing as well. So in this case, we're doing exactly the same test. There's 500 impacts, but we're just changing the size of the region that we're doing those 500 impacts over. So it's all done automatically in the instrument software. You go away and set all of this up, it'll come back and do all of it together. And what we can see here is as we move from left to right, then we're decreasing the test area size. And now what we're seeing is that we're getting this complete destruction of the surface, and we're getting this real fine scale debris that we saw earlier with the yttria-stabilized zirconia in the cross section. We're seeing that very fine scale debris. And then you're seeing So you just see the last few impacts. The rest of the surface is basically covered up by the remains of this small scale debris. So the thing we can do is we can quantify the damage. So these are laser scanning confocal images again. So what we have here is 150 impacts on the gadolinium zirconate, and on the left is a rectangular distribution, and on the right is a Gaussian distribution. And we're having a bigger volume, looks like it's about double on the right for the Gaussian. So, and we can track that in the middle with looking at, say, the final depth as a function of number of impacts. And you can see there clearly there's a clearer transition towards this bigger damage regime for the red, for the Gaussian distribution one. You can see on the right that there's a region of that material where it's been completely destroyed, and it's much less on the left. Similarly, we can look as the effect of load. So on the right, we have at 500 millinewtons, and on the left, we have at 1 Newton. And again, at the higher force, we're having a much bigger removal of material, and we can see that quite nicely again in how the residual depth tracks as a function of impact. So at the higher force, you can see in the red there, you're getting that transition occurring more extreme and more rapidly than at the lower force. So we have a very nice sort of quantitative control on understanding what's going on. So another thing we can do is we can obviously compare across the two different materials. So here, these are rectangular distributions essentially. So there's 7 YZ at the top there is by far the most impact resistance, as the lowest volume. But if we run it on and look under more comparative, more severe conditions, in this case, with the Gaussian distributions, then we're getting a sort of about a 3-to-1 difference between those two. And that is broadly in the range of what you see in erosion, real erosion tests, where they're typically around sort of 4 to 6 times difference for typical samples. So then, next step that we thought we would do is to extend all of this to high temperature. So this on the right is just a zoom in of a little part of the instrument showing a hot stage there. And in this case, we can use this hot stage to heat up the sample up to 850 degrees. And then we can do our repetitive randomized impact tests, and just in the same way as we do at room temperature. So here's some examples back to fused silica now. And as we go through that temperature range, we change the mechanical properties of the glass. So the hardness modulus ratio changes as well as it softens a little bit. And what this results in essentially is changes in brittleness of the glass, and also changes in how those crack systems develop. So these are examples just at the same position. What we can see here is at 830 degrees C, here on the right, we're getting, it's more crack tolerant essentially, so that there are more impacts needed, and the progression, once there is a bit of cracking, that progression is more gradual than it is more sort of abrupt and sharp on the left. So back to the TBCs. So here's some examples. So the TBCs are considerably less exciting. So it's a system as a function of temperature. So you can see there, so the green is at room temperature, the red is at 850. And in terms of the final depth, you can say, well, actually, it's going in more at the higher temperature. But actually, if you focus on the amount of damage, then actually after the first impact, it's not so different. So there's a softening and difference initially, but if you focus on the damage tolerance afterwards, that red curve essentially, the change in slope after that is if anything, slightly less than it is at room temperature. And this sort of thing does correlate fairly well with what you see at room temperature for 7YZ, for high temperature erosion tests, essentially. So there's not much difference in room temperature between room temperature erosion and the high temperature tests. And that the differences that are there are really often related to differences in the velocity, essentially, in the erosion test, because typically the high temperature erosion tests are a little bit faster. And that does increase the erosion rate. So we can also do some, just as at room temperature, we can do these randomized tests. There's just some examples there with different sized randomized tests. In this case, 100 tests here. My colleague Josh did this work. And here, again, we can do things like track the residual depth as a function of impact, and we can understand transitions and things and how those are affected by temperature. So it's quite a powerful test because we can do exactly the same things as we can do at room temperature. Okay, so that's just to that's really it from me. Just really to introduce this new test technique. Say it's got a lot of potential, we hope, and we settled on calling it randomized impact because statistically distributed didn't sound quite as exciting, but we're interested to hear if you think that's a misstep. And certainly from what we've seen so far, it's got very strong potential because it shows very good correlation with real erosion tests. And it's so much simpler to do. All of these tests that we've shown are really very quick, the order of a few minutes. And we can do this, extend this test recently up to 850 degrees. And I'm sure we could go much higher in future if we just set our minds to that. So that's all possible. On the right, you can see there that all of these different types of tests, we can track all these different metrics such as depth and coefficient of restitution and energy loss. And that really allows us to build up real pictures of how different material surfaces either become more damage tolerant or not. And I'll just finish with this one as a challenge. Sam said it as a workshop, so you're not going to get away without any workshop related activity. So if you can look and try and choose, 2 of those images are real impact tests and 2 of those images are real erosion tests done at Cranfield. And in this case, this was not on either of those 2. So this was on an optical coating system, which had a relatively poor adhesion due to a plasma clean issue, which they then fixed. So if you want to, by all means, have a guess on the right, and we will mark them later. Okay, thanks so much.
Thanks, Ben. Always good to have a little bit of interactivity in these. So yeah, please, put your guesses in the chat, and we can have a look through these, through the answers in a moment. But what I will do now is, just before we begin with the Q&A, is release the link for the attendance certificate, which you can download now. So please click on that featured actions link. So just to make it clear to everyone, this will only be available in this event. So if you want the link, please, or if you want the certificate, sorry, please do click on the link now. The link will still be active for the next day. So, click it, open the tab, but come back. We're not finishing just yet. We still have quite a few questions to get through. Okay, so we have our first guess. So Suresh has said the right hand is erosion.
And Suresh is right. So
there we go. Right, just to make it clear for anyone who's asking, that link right there that I've also put in the chat. You can also click just in the bottom left-hand side of the screen. It might be displaying differently if some of you are joining on mobile devices, but should still be there. Okay, so with that, let's begin to work through the questions. So we'll go with. It's not working now. Oh. Right. It's not working now. Does it work later? It does work. I've just opened the link myself, and it is there. So when you click on it, It will ask you for first name, last name, and email address. Okay, and then what it will do is send you a PDF of the attendance certificate to email. So, Brittany, please, do try the link again. I will have your, from the registration, I will have your email address, so I can. Okay, so if you can try again in a few minutes, if not, I can follow up after the event just to make sure you can get your link. So I'll just make a note of that. So, okay, let's begin with the first question. So we'll go with oldest question first. So from Maxim, who asks, how do you take into account the formation of the mechanically mixed layer, mixture of test material, erodent particles, oxides, etc., that can lead to an increase in hardness or other properties? I think this is when you were first talking about the structure of the thermal barrier coatings, Ben.
Well, yeah, that's an interesting point to some extent. I mean, so certainly. Sorry, you lost me there, I think.
No, there we go. You're back now. I can hear you again.
Yeah, apologies, something happened. Yeah, in erosion of TBCs, then, I mean, alumina and things like that, you don't tend to have these sort of mechanically mixed layers. You may get that with sort of silica type erodents. So, I mean, I think the answer is, how would we do it? Is we'd essentially maybe have different types of indenters and things like this. So in this case, we wanted to simplify the test and have to correlate with alumina. So we had a harder indenter, much harder indenter than the material, but it would be just as possible to have potentially sort of the indenters that might be deformable as well. So these things are all possible. But equally, the thing about increasing hardness, well, I mean, it's also something where we can use this type of test to look at maybe the effect of, or simulating a shot peening process. It's not just related to erosion. There's a number of sort of other site applications. Even people have suggested micro pitting, also interrupted cutting type situations. There's quite a lot of different applications essentially. I don't know if that's quite answered it, but that's off the top of my head. That's kind of what I'm going to say.
Yeah, I mean, I think, yeah, effectively, it's very system dependent, really. So it's, the nice thing is with it, as you're testing on a multifunction instrument, really, you can do the erosion test and then swap to another test technique, like you said, with, do indentation post test and so on. Okay, so let's move on to the next question from Udaya. I hope I'm pronouncing that correctly. So, do you have any test that is abrasion and erosion combined?
Well, yes. Well, all of the tests I showed here they were normal impact, so 90-degree impact. But we have adapted it to do angled impact, which I think does catch much more of this abrasion erosion combination. So, and that works very nicely as well. So yeah, that works fine as well. So you can do off angle, and we've done even up to sort of 50 degrees or something like that, or something like that. So these are all possible. Different choices of different probe geometry. So I suppose that's the other thing I didn't say is that by simply changing the sample orientation, you can easily look at lots of different tests. And these things are very quick tests, so you can get these big matrices of results much more easily, and with hopefully more sensitivity to. You could look at thin coatings as well, all sorts of things.
Okay, very good. Thanks, Ben. So next question from Robert, who asks, what is the impact frequency during the test?
In this version, then we were doing this around 1 hertz or something like that. So half a hertz to 1 hertz, something of that sort of frequency. So there is another way we can do this with a sample piezo behind the sample and do it that way, that would be more complicated, and that's something else we could do. That would allow us to access higher frequencies, but for this type of test, just these frequencies are around 1 hertz, and we cause an awful lot of damage very quickly. So that's where we are with it at the moment.
Okay. Got it. Okay. I'm just thinking back to when I did some of this. So is the frequency, is the available frequencies increased then since?
Yeah, yes, a little bit. Yeah, a little bit. Well, one of Thomas's colleagues wanted us to go a bit faster or something.
Mm-hmm. Yeah, no, it's just just mentioning my my PhD work later, and then just sort of thinking back to kind of what I had set for my things. But yeah. Okay, so let's move on to the next question from Sankara, who asks, impact is unidirectional. The erosion occurs multidirectionally. How would the correlation work?
Well, I think it does, but equally at any there's a dominant, even if there's multidirectional, there's a dominant gas stream. And there's a dominant particle stream, so there's a dominant angle of attack that you simulate with any one test. If it's a 90-degree impact, you simulate with a 90-degree erosion, you simulate with a 90-degree impact, and vice versa. Say if it's a 30-degree erosion test, you'd simulate with a 30-degree impact test. There's presumably all sorts of clever things you could do by moving the sample staging between impacts, but I think that would just add more and more complexity. All of these things are possible because essentially the sample is sitting on a stage that you have independent control over. So there is a certain amount of flexibility.
Okay, so yeah, it's very much how much the user would want to program into their experiments. I guess the software fully allows for this stage movement between any impacts anyways, because you can make that XY adjustment for doing the grids as you've shown.
Yeah.
Okay. All right. Thank you. A question from Suresh, who asks, please can you elaborate on how the kinetic energy absorption is calculated?
That's a good question. Can I even remember how there's an MIT paper that follows an analysis by Andrews, and that's where it's taken from essentially. But we've used we calibrate the mass, the dynamic mass of the system. We have the velocity in and the velocity out coming direct from the curves. So with the mass, we can determine the kinetic energy in and the kinetic energy out, and from that we can say the kinetic energy loss. People have also done potential energy and things like that. I didn't in this, but certainly Janet and co-workers at MPL have done it that way as well. So there are quite a lot of different options. But the kinetic energy absorption or kinetic energy loss works quite nicely. But you do need to calibrate it for the mass. So that's.
Got it. I was trying to see if I could find that paper quickly to share it, but I think that might take a little bit of time. So it's best we proceed with further questions. Thanks, Ben. Okay, so I think we've somewhat answered this before, but one from Michael here, who asks, in sort of old-fashioned erosion thinking, we learned that angle of attack is important. Your tester is only loading perpendicularly. How do we now forget about the direction of impacting?
No, it's a good point, isn't it? As I think I'd said a little bit through the questions, that there's always a predominant version, and I think the easiest for us to do on a test thing is to change the angle and then do everything under that dominant. So the mechanical, how much is cutting and how much is plasticity. This seems to be the heart of what causes these differences in brittle ductile deformation. But we can do all of that, and we can get the same level of sensitivity to brittle ductile transitions with angle as well. And indeed, we have actually done tests at different impact angles and then correlated that to models at Cranfield as well.
Okay, thanks. There you go. So yeah, it's all possible. Just
it's all possible.
Yeah, really just depends on. It's just, I think, as you said many times, Ben, it's just increasing the complexity of the test then. So, but
yeah, from an instrument development point of view, it's always a challenge that you have to work out how much to increase the complexity. It's an advantage for somebody and it's a disadvantage for somebody else. So we just try and increase the flexibility, and then from that, it's up to people which route they choose.
Yeah. Got it. So I think we've got a question from Sankara here, who asks, is this test methodology accepted by aerospace industries for evaluating the high temperature erosion resistance of thermal barrier coatings?
Well, it's a new method, isn't it? So the aerospace industry is notoriously conservative, because at the end of the day, we don't want our aeroplanes falling out of the sky. So so aerospace is particularly conservative, but I would say that what we're trying to do here is provide a tool that allows us to develop coatings more rapidly. So that's to cut down, to streamline these coating development processes. We have these very, very long and complex coating development cycles that are very expensive. So when we're talking often to Cranfield and Rolls-Royce, they're very much saying we develop these great coatings, but it just takes a long time, and it's difficult to know where. Yeah, and also they're dealing with rare materials as well. So none of this is simple, but we've simplified that whole thing, get a lot of metrics out quickly, and we have that understanding. And then for your safety critical applications, then you're going to use the actual.
Oh, sorry, the connection just dropped out for a second there, but yes, it's okay. Perhaps just expanding.
Is it back? Sorry.
Yes, yeah, I can hear you again. Yes, sorry, it just drops out for a second, so I think we dropped the last word of that answer.
All right, sorry, it just says a stream of collection lost in my thing. Yeah, apologies. I think I'd kind of got to the end, which was just that.
Oh. There we go. We're back.
We're using this thing very much as a scoping and type test rather than the end result.
Sure. Just expanding off of that answer, and this may be a little bit outside of kind of the scope of the test equipment at the moment. Do you think there might be some room for a standard utilizing this equipment and this methodology in the future?
Well, you hope so, but usually when you have standards, you need quite a lot of different manufacturers to group together and say it's a great idea. And when you have something that's unique, it's a little bit more difficult to get it standardized. So there's always the competing pressures.
Okay.
So yeah, I mean, we talked about erosion very much today, but as I say, we've sold this thing for PVD coating development primarily, for a range of different applications to various different companies, and unfortunately we can't say anything about it because they have a commercial advantage by having this instrument, and therefore they would rather just keep it as quiet as possible.
Yeah. Yeah.
So, and that's where we are. So
got it. Thanks. Okay, so unless anyone else is typing any questions at the moment, I've got two more remaining from Khaled here, who asks, excuse me, in the case of multi-layered specimens, do you think the mechanical behavior, ductility and rigidity of the supporting layer could affect the results of your test? Sorry, Ben, did you hear that okay?
Well, I'd say in the sense of it's a multi-layer system. Yeah, I did think so. In a multi-layer system, then I think that the sensitive to the mechanical properties across the different layers in the system, just as you are in anything like a scratch test or an indentation test or anything like that. The system itself, the instrument is effectively perfectly rigid as far as it's, or at least sufficiently rigid as far as concerned. But if you put the same very hard coating and you put it on had a compliant sublayer or a non-compliant sublayer, then you would be very sensitive to those different mechanical properties, and you can model that out quite clearly. Because that's what you would see in the real erosion test as well. So it's exactly the same thing.
Okay, very interesting. Thanks. Okay, question from Jan here. Who says, "Nice talk. How much can the initial impacting strain rate reach? What is the range of impact energy?"
The energies are small because they're over. You're using small forces and experimenting to really small distances, but you're dumping that into a very, very small area. So the strain rate density or the energy densities are very high. In terms of actual strain rates, it's something like approaches 10 to the 5 on contact per second. I think that it was I don't know. It was about slide 5 or something. I don't know if it's easy to go back or not go back. But
I can scroll back quickly.
if you
take a look at that.
I'll tell you if it's 5 or not 5. That one.
Oh,
Yeah,
there we go. Sorry.
1 4.
That should be it, Ben. Sorry, I think we're just having some connection issues again, everyone. Apologies for that. Are you back, Ben? Can you hear me?
Sorry, we're having a little bit of issue.
There we go. The the treacheries of doing things live, really. But yes, we're back. We can hear you, and we're at the correct slide, I believe, now.
Yeah. So about approaches 10 to the 5 on contact. Or can I mean, it's a little bit dependent on probe geometry as well, so it's not quite as high as that if you have very large spherical probes, but otherwise it can be pretty high.
Got it. I think we'll take what I think will be the final question here from Sankara, who asks, "Poor adhesion, a reflection of the integrity of the base coat or the top layer?"
Well, in the example I showed right at the end, that what I said about poor adhesion, that's just it's a multi-layer. I think it's a multi-layer optical coating system, but essentially it's the poor adhesion in that case was caused by an ineffective plasma treatment. A plasma cleaning step wasn't working quite as normal, and so then when the coating was deposited, it wasn't deposited with the same level of adhesion essentially. So this company they work with are very good at that normally, and they knew they had a problem. And it was just an interesting sample to look at sensitivity for, essentially.
Okay. Great. Thanks, Ben. Thanks for answering all those questions. So I think with it now being 4 p.m. UK time, I think it's now a good point for us to draw the webinar to a close. So just move on to our final slide. So thank you very much, everyone in the audience, for all of your great questions, great discussion there. Just before I begin my outro speech, excuse me. To question there about accessing the webinars on YouTube from the website. So if you go onto the Surface Ventures website, surfaceventures.org, and scroll down, you will see all of our recordings. You can also search Surface Ventures on YouTube, and all of the recordings are there. Getting mixed up with things I've been saying in the questions. So sorry about that, everyone. And from Micromaterials. So It's a good point for me to share that. So there's a link now present for the Micromaterials LinkedIn page. And of course, you can also visit the Micromaterials website, but the LinkedIn page is great for technical articles, links to other webinars, and basically a lot of technical material. So please do click on that. Thank you very much, Ben, for your fantastic and engaging talk, and for answering all those questions. Thanks to Micromaterials for the support for running this workshop. As well, for other links to share, please do register for our final keynote talk of the year, Surface Ventures. You can also find the link to this on our website. This will be on the 14th of December. As well on our website, so stay tuned to our emails. Check out the Surface Ventures LinkedIn page for updates. We also have our fortnightly newsletter, Modern Surface, the final issue of the year, releasing this Friday. We'll then be beginning again in January 2024. By signing up to our mailing list, you will receive this. And finally, I'd just like to say, thanks everyone, but please do take the time to advertise this to your contacts if you think this will be useful to them. It's great to continue to grow our audience and make more people aware of the work we're doing here. So see you next time. But for now, thanks everyone for joining today, and have a great rest of your day.
Yeah, thanks very much. I'd like to echo and say thanks very much to Sam for hosting as usual, and thanks everybody for the questions, and hope everybody found it useful. Okay, thanks. Bye-bye.
Fantastic. Thanks, Ben, and goodbye, everyone.